Did I think I messed up where I was writing the answers to some of the problems on like 8 point, let's see, no, it was 8.23 and 8.24. I did. I messed up. I don't know how I did that. I don't know what I did. So we'll just do like 8.23, 8.24. We'll do any of the ones that I messed up. Did I mess up 8.25? Anybody tell me?
Oh, I remember she did one of the like an even or something. You were supposed to
Do an odd. I know. I got mixed up. It happened. So we'll have to we'll just do some. Doesn't matter which ones we do, so long as you get the concept, you know. But it's all good. So make sure you've gotten your exam. Yep, so exams are at the back, and stapled to the very back of your exam is your grade sheet. And when you're all done with them, you can put them in the red basket. The red basket are exams that people have already looked at. So all the other exams are laid out in alphabetical order. Okay, so we got one more minute. Okay, so make sure you get a chance to look at your exam. It was a 4-point curve on this exam. So there was a curve added to it. So you look at the score on the very last page, and then it's 4 more points, and that is what is on your Moodle grade. Okay, any questions about that? Okay, and y'all know that drop day is coming up. It's November 30th, right? So now you have kind of all your updated grades. You can make those decisions if you need to. Hopefully not many have to. Okay. Don't forget to sign in on the sign-in sheet. So if you haven't done that yet, please go ahead and do that. What did the pig who got stuck outside say? I'm bacon. My son really liked that one because he really likes bacon. Okay, so we got some iClicker questions. Y'all ready for some iClicker? Let's do this. All right, here we go. Remember, you can have your notes out for this. A mixture which has evenly dispersed substances is called a blank mixture. Remember, you got 1 minute. Okay, 5 seconds. Make sure you click in. Okay, turn and talk to the people around you. See what they come up with. Oh, I got something on the chat. Okay. Yeah, 30 seconds on this one. Should get this one. 30 seconds. Okay, so what did we say? Good, it should have been homogeneous mixture. Okay, and we did go up, very nice. So if it's all the same, it is homogeneous, right? So it's the evenly dispersed that makes it homogeneous versus heterogeneous. So that leads us into the next one. I always forget that I have like the answer there. A cup of coffee with sugar is a homogeneous mixture, but as scientists, we call it a blank. So you're referring to the cup of coffee with the sugar in it. One minute. Okay. Talk around you. Decide on another answer. Don't forget to click in again. Seems like everybody's done chatting about it. Okay. Make sure you click in again. I'll call it at 45. Okay, so what did y'all say? So it is correct, it is C, a solution. So we definitely increase that. So when we were looking at this, right, the one that you should look at were colloid and solution, right? A solvent is just one thing, right? So you can't say solvent, and a solute is just one thing. You put the solute in the solvent and you make a solution, right? But now here's a question. Is it a colloid? Why is it not a colloid? A colloid is cloudy, right? So if we talk about the difference between a solution and a colloid, a solution is going to have to be clear, right? Everything's going to dissolve inside of it. With a colloid, you have some particles that are small, but that don't fully dissolve, right? They're small in size, so they're evenly distributed and they don't settle, but it's still cloudy. And so coffee with sugar is not cloudy. Coffee with milk would be a colloid, right? Okay. Oh, and we did that, so I'm not going to do that again. All right. Which of these is a colloid? Which of these is a colloid? Okay. All right, we got 1 minute. So turn, talk to people around you, come up with a second answer. Make sure you click in again at 45 seconds. Please make sure those masks are up and covering noses and mouths. Noses and mouths, please. Okay. Oh, and I'm not watching my time. Okay. So what do we say with, what is A? Ampicillin in a liquid that must be shaken before use. That means it settles. So what do we call that? Suspension. Good. Pedialyte, a clear liquid. What's this one? Solution. Fruit and yogurt smoothie, a chunky, thick, turbid liquid. Is it going to eventually settle? Yeah, you got big, chunky things inside of it. So what is this? A suspension. Lemonade, a cloudy liquid. This is a colloid. Vinegar, a clear liquid. Solution. Okay, so you should have said B. All right, so let's see, what did we say? D, oh, not too many. Oh, and we went up. Very good. So we were definitely between the two. But you got to think, what's the difference between C and D? One's a clear liquid that's not going to settle, and one will absolutely settle. It's all about the size of the particles. What are the size of the particles in a suspension? Really large. What are the size of the particles in a colloid? Smaller. Okay, that's your difference. Okay. Oh, one more. I forgot I got one more. Okay. Now, this is just like the problems we were doing yesterday. This says to select the correct products for the balanced chemical equation for the hydration of Na3PO4. I am going to suggest that right now you take out a sheet of paper. I'll give you 2 minutes on this one. Take out a sheet of paper and hydrate Na3PO4. Don't look at your answer choices until you do the problem. Okay? 2 or 3 minutes. I'm kind of checking and see how y'all are doing. Okay? So go ahead and do it. Write it down. Don't try to look at the answer choices right away. write your equation. So just hydrate Na3PO4. Bless you. Please make sure those masks are covering noses and faces and noses and mouths. Coming up on 2 minutes. Raise your hand if you need some more time. Okay. You got some more time. So I'll close it at 2 minutes, 3 minutes. I mean to say 2 minutes, I meant 3 minutes. Bless you. Okay, 15 seconds. Make sure you don't leave it blank. Take a guess. Five seconds. Okay, turn and talk to your neighbors. I'll give you 45 seconds to talk. I will write it. Okay, 5 seconds. Make sure you click in again. A few people haven't. Click in again. Okay, so what did you do to do this problem? You put an arrow and you put water, right? Now, this Na3PO4, I didn't give you a state of matter, but you can assume it's a solid, right? We're going to put it in water and it's going to dissolve. So what is it going to dissolve into? Na and PO4. So Na is a metal, and then PO4 is a polyatomic ion. Do we split up the polyatomic ion? No, always keep your polyatomic ions together. So we're going to have Na, it's going to be aqueous. We're going to have the PO4, it's aqueous. What do we need? Two things. We need charges and we need to check to see if it is balanced. So what's my charge on sodium? I just go to the periodic table. I'm a +1. PO4 is a -3. So now I got my charges. Am I balanced? No, what do I have to do to be balanced? Put a 3 in front of Na. So these should have been your products. So that should have been answer choice B. See how B and C are the same, except C is not balanced? Okay, so let's see. So it should have been B. Okay. All right, so we definitely made a big improvement there. So are you gonna have to do that on the exam? Yeah, absolutely, absolutely. So if you're having trouble with this, you're struggling with it, please come see me now. Don't wait. Please don't wait. Okay. Let's go to our in-class problems. Okay, so in the video for starting on 8.4, I started doing, I think, the wrong evens or odds. I don't know what I was doing. So we're just gonna do some, okay? It's all good. We're just gonna do some. So what is the concentration in millimoles per liter of a Ca2 plus solution that is 2.5 milliequivalents per liter? So when you're reading these questions, probably the most important thing is to figure out where to start and where to end. So what's our starting point? $2.5 milliequivalents per liter is our start. Where's our end? I want concentration in millimole per liter of a Ca2 plus. This is our end, right? So when you're doing your dimensional analysis, you want to make sure that whatever you're supposed to end up with is what you really end up with. So we're going to start with 2.50 milliequivalents per liter. And I want to get to millimoles per liter. There's a long way and a short way to do this. Okay. When you see milli, what does milli mean? 1/1000, right? That's what milli. So milliliter, millimole, milliequivalent, it's all the same. So you could either use dimensional analysis and get out of milli and then go back into milli, or you could realize that milliequivalents and millimoles, the milli like cancels itself out. Yeah. So if I know that I have a relationship between milliequivalents and moles, right? Because that's the definition of it. What's my definition of equivalence? So if I have Ca2 plus, right? 1 equivalence of Ca2 plus is equal to what? Oh, I'm sorry, I didn't mean to put the 1. We have how many milliequivalents of Ca2 plus equal to what? Equal to some number of moles of Ca2 plus. So what goes in the blanks? If I have 1 mole of Ca2 plus, how many total charges do I have? 2, because it's a plus 2. So I have 2 equivalents of Ca2 plus per mole. But I can say the same thing. I can say I have 2 milliequivalents of Ca2 plus for every 1 millimole of Ca2 plus. Do y'all see that? So you could use this or you could not. It doesn't matter. But I'm going to do the short way because as long as milli's on both sides, it works, right? So if I put milliequivalents on the bottom, Ca2 plus, right? So if I have 1, oh no, not 1, 2. If I have 2 milliequivalent Ca2 plus for every 1 millimole of Ca2 plus, right? So now what are my units? I've canceled out milliequivalents. Now I'm in what? Millimoles per liter. Is that what I want to be in? Yeah, did you see how I could do that in fewer steps? It doesn't matter how you do it. So 2.5 divided by 2 should give you what? 1.25? Not milliliters. moles Ca2 plus per liter. Okay. Good. All right, let's do 8.24. What is the concentration in milliequivalents per liter of Mg2 plus solution that is 100 millimoles per liter? So where's my start? Where's my end? My 100 is my start, and my milliequivalents per liter of Mg2 plus is my end. Do I have an equivalence that I know? By definition, what do I know about Mg2 plus? For every 1 millimole of Mg2 plus, I have 2 milliequivalents Mg2 plus. I'm running out of room. Plus. Yeah? So then start with, I'll start a different color. Start with 100 millimoles per liter. So now I'm going to do my conversion that I had over there. I have for every 1 millimole, because I want to make sure that my units cancel, I have 2 milliequivalents Mg2 plus. So my millimoles cancel. I'm left in milliequivalents per liter. Is that what I want? Yeah, it is. So 100 times 2 is 200 milliequivalents Mg2 plus. Okay. 8.25, what is the molarity? What is molarity? When it says, what is the molarity? What unit am I looking for? So look at your best friend. Look at your best friend. What do you have down here? The sheet with all the equations on it? What's at the very bottom? See, it says solution equations. What chapter are we on? Solutions. So this is where you're going to find the majority of what we're going to use on the best friend. So do you see something that's molarity? What is molarity? It is in moles of solute over liters of solution, right? So the molarity that we are hunting for, our goal, our end, is in moles per liter. That's what we want. But what are we starting with? 250 milliliters of solution with 4.20 moles of ZnCl2. Okay, so let's put those two things together. If I have 4.20 moles ZnCl2 per 250 milliliters, what do I need to convert? Milliliters to liters. Do I have to do anything with the moles? No, because that's what I want. I want moles. I want moles per liter. I'm sitting in moles per milliliter. So now I just need to get rid of the milli and say there are 1,000 milliliters in 1 liter. And now my milliliters cancel. I'm left in moles per liter. So 4.20 times 1,000 divided by 250, what do you get? 116.8 moles per liter of ZnCl2. Now there's another way that the book will write this sometimes. Let me do this for you full screen. Okay, there's another way that the book writes this. If we're talking about molarity, you can write this as 16.8 big M ZnCl2. The big M represents molarity and it represents moles per liter. So you can see it as either way. Okay, so just be aware of that. All right, again, what is the molarity of 750 milliliters of solution containing 2.10 moles of Na2SO4? So we're looking for the same thing. We want to end in moles per liter, just like we did the problem above. So if we have 2.10 moles of Na2SO4, and that is in 750 milliliters, I only have to do the same thing. I'm in moles, that's great. I want moles, but I want per liter, not per milliliter. So I got to get rid of the milli. So 1,000 milliliters in 1 liter. My milliliters cancel. I'm left in moles per liter. So what do you get? 2.8. Now, you could write it two different ways. You could write 2.8 moles per liter, or you could write it as 2.8 molar Na2SO4. Molar and moles per liter is the same thing. Okay. All right. I think I did 8.27 in the video, correct? Yeah. Question? Good. Okay. All right. What is the potassium ion molarity of 850 milliliters of blood plasma containing 10 dot? What does that mean? Why is there a dot there? That's telling me that that 0 is significant. So my answer can have how many significant digits? 2. If the dot weren't there, how many significant figures would I have? Only 1, right? Only 1. Okay, so what are we going to start with? Our millimoles per milliliter is what we're going to start with. Where are we trying to go? We're trying to end in molarity, which is moles per liter, right? That's moles per liter. So we have 10 millimoles, K plus, in 850 milliliters. So now what am I going to do? You need to convert to moles. So you're going to realize something when we're done with this that's super cool. But I want to let's get to moles first. So I say 1,000 millimoles in 1 mole, right? So now I'm in moles, that's great. But I want moles per liter. Do I have liters? No. So I'm going to convert 1,000 milliliters in 1 liter. So now my milliliters cancel and I'm in moles per liter. What did we just do? We divided by 1,000 and then we multiplied by 1,000. So did we actually do anything? No. So if you have milli on top and milli on bottom, millimoles per milliliter is the same thing as moles per liter because the millis cancel out. Isn't that kind of cool? You don't have to remember that, but it's nice. It's a neat trick, right? Okay, so all you really had to do was divide 10 divided by 850. So what do you get? Should be pretty small. 0.012 molar or moles per liter, however you want to write it, K plus. Yeah. And the odd ones are done in the video, but they're not done here because I don't know how I saved it. I don't know what I did. It's one of those days. It's one of those semesters, right? Okay, so we're doing the evens because the odds are in the video, right? Yes. Okay, I always get mixed up. How many grams of NaCl must be added to water to create 2 liters of a 0.54 molar normal saline solution? All right, so You can do dimensional analysis. It's the same thing. You just have to know what you're starting with and where you're going. So where are we going? Where's our goal? I want to know grams of NaCl. This is my goal or my end point. Whatever you want to think about that. So I want to know how many grams if I'm going to make 2 liters of a 0.54 molar normal saline solution. So how do I start my problem? What does the big M mean? It means moles per liter. So what I really have is 0.154 moles per liter of solution. But am I making a liter of solution? No, what am I actually making? I'm making 2 liters. So all you have to do is multiply times 2 liters. Are you always going to have something at the bottom in a dimensional analysis? Not always. Not always. Okay, so now I'm in moles, but do I want to be in moles? No, I really want to be in grams. Can you go back and use what you learned before? How do I convert from moles to grams? I got to go find the molar mass of NaCl. How do I do that? Molar mass is grams per mole. I have to go to the periodic table, right? Go find Na. What is Na? Molar mass is our grams per mole. So how do we get this? Go find Na. What's my mass of Na? 22.99. And how many do I have of sodium? Only 1. So multiplied by 1 is itself. Chlorine. What's my molar mass of chlorine? 35.45. So add those 2 together, what do you get? .44 grams per mole of NaCl. So just go and plug that in. 58.44 grams per mole of NaCl. So what cancels? Moles, and I'm left in grams. I'm left in grams. What do you get? Calculator clicking, favorite sound ever. What'd you get? Come on, y'all. 17.1. I got 18. Everybody get 18? Okay. So 18 grams of NaCl. Okay. Yeah. All right. Now, sometimes we are given concentrations of things in percentages, and there are a couple of different ones. So if you look on your best friend, everybody take out your best friend right now. There's percent concentration, which is parts of our solute over parts of solution. That's one way to do it. You could do percent in mass by volume. Do y'all see what I'm doing? Are you on your best friend? Right? You have percent mass by volume. Mass by volume is grams of solute over milliliters of solution. So you have to go and get this formula. Are you going to have this formula on the exam? Yeah. Mass by volume is grams of solute over milliliters of solution. So that's okay. It happened to me when I was an undergrad. I was actually in my advisor's, like I did research in his lab and everything, and I was in his class, and we had just gotten phones that could play songs. Okay, this is how old I am, right? And this is how much of a nerd I am. My phone started playing the Star Trek theme song in the middle of class. Dun, 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 dun. It was great. It was great. So trust me, whatever it is, I've experienced worse. Okay, so A, 75 grams of Na2SO4 in 250 milliliters of Na2SO4 solution. So how do I calculate the percent mass by volume for that? All I have to do is plug in my numbers, right? And then as I was telling my story, I forgot, multiply by 100 to get a percent, right? Okay, so you have 75 grams, that's our solute, right? Divided by 250 milliliters of our solution times 100, what do you get? So we got to go 2 sig figs. What do we get to 2 sig figs? I got 30%. Now, when you say 30%, if you just put the percent, you're not being very specific. What do I need to put here? 30% mass by volume. Okay. B, 39 grams of sucrose. It's easy when all you have is one is a mass, one is a volume, right? You know which one's which. The mass, the grams goes on top, the volume goes on bottom. 355 milliliters times 100 gives me what? I get 11%. Is that what y'all got? Mass by volume. Now it's the mass by volume of what? You're saying that the whole thing is 100%. And 30% of it, mass by volume, is the solute. So 30% is Na2SO4, or for B, 11% is sucrose. Okay. All right. Okay, so that's not the only way that you can find concentration, right? There's concentration in mass by mass. So when you're doing concentration of mass by mass, you have to be a little extra careful, right? Because look at your equation for mass by mass, right? Our mass by mass is percent mass by mass equal to grams of solute over grams of solution times 100. What is a solution? It's a solute dissolved into a solvent. So the solution is both the solute and the solvent. So if I do this problem, I'm telling you, this is where people mess up. Mass by mass. Grams of solute. Which one is the solute? KCl or water? KCl, it's less. Over, am I just going to put 100 down there? No, because that's the solvent. Is it the solution? No. So what do I put at the bottom? I put 100 grams water plus 10 grams KCl, right? So I got 10 grams KCl over 110 grams of solution. So what do you get when you plug this in? How many sig figs? 3 sig figs. Should be almost 10. What do you get? I got 9.09% mass by volume, mass by mass. Is that what y'all got? Okay. So be careful. I'm telling you that lots of people will put 10 over 100 and go. And I'm telling you that will be an answer choice on the exam. So make sure you don't miss that. All right, 8.36. How many grams of NaCl must be combined with water to prepare 500 milliliters of a 0.9% mass by volume physiological saline solution? Why do we call this physiological? What does that mean? What does the word physiological mean? This is what is normal for our bodies. So if you have a physiological saline solution, well, that's the saline solution that should be in your blood, right? So when you're making an IV, if you want it to be equal, if you want the concentrations to be equal, you want to use a physiological concentration, a concentration that the body physiology normally has. Okay, so our goal is to get to grams. This is our goal. All right. And we want to know how many grams of NaCl must be combined with water to prepare 500 milliliters of a 0.9% mass by volume physiological saline solution. Now I'm being given the answer, right? Remember our formula? I'm basically being given the answer. I'm being told I have a 0.9% solution. Mass by volume. What goes on top? Grams of solute. But in this case, what is our solute? Let's say that. Our solute is NaCl, right? And we're putting it in water. How much water are we putting it in? We're putting it into 500 milliliters, right? Okay, so times 100. So basically we have an X right here and we're solving for that. Can you solve for that? You know what to do? So some people say cross multiply, some people say all kind of different, but what I do is I do the inverse of whatever is next to X. And what I do to one side, I do to the other side. But it doesn't matter, however you want to get there, right? So what do you get? I got 4.5 grams NaCl. Yes? Check my math. Okay. So there's a third way. There's molarity, there's percent, right? And then there's a third way to identify concentration. The other way that sometimes we list concentration is in parts per something, right? So a lot of times we do this for things that you only have a few of. Like, for example, we test our drinking water for fecal coliforms. You know what that is? Bacteria that you find in poo, right? Do you want to have a lot of fecal coliforms in your drinking water? Yeah, no, we really don't. So a lot of times you have water testing that will say, okay, there's a threshold of how many fecal coliforms can actually be in the drinking water. Otherwise, it's going to make people sick. Rightfully so, right? So you want to have very, very few parts per billion, right? For something like that. But it depends on what you're actually assaying for, what the concentration should be. But another example, if you're have drinking water, you don't want a lot of impurities in the drinking water because people are putting that in their bodies. So we could look at copper. Copper is not supposed to be there, right? So when we say not supposed to be there, there's going to be a little, right? It's running through pipes and things like that, but there's a threshold. So what's the concentration in parts per million of a solution containing 1 1.50 milligrams of copper and 100 milliliters of water. So how do we do that? Go to your best friend. Go to your best friend. There's a formula for parts per million. What's the formula for parts per million? It's equal to what? Grams solute over milliliters solution times, is it 100? No, it's a 2, 3, 1, 2, 3, so 1,000 million. So what is percent really? Parts per what? You know this. You know this. You don't realize you know this, but you know this. If I said it's, if I multiply times 100, like all of our other percent things, right? Grams per milliliter times 100. This is a percent, but another way I could say this is parts per 100, right? That's what the parts per is telling you. So everything that we normally do in our everyday lives that is percents is really parts per 100. What we're just doing is instead of multiplying by 100, what are we multiplying by here? A million, so it is parts per million. If you wanted parts per billion, what would you do? Multiply by a billion, right? Not a big deal. Okay, so what's our grams of solute? Now be careful, it's grams of solute. So if I put 1.50 milligrams, is that correct? No, it's not. What do I need to do? I need to convert that. So I'm going to say in one, I have 1,000 milligrams in 1 gram. So divide that, what do you get? Just move your decimal place 3 times. You get 0.00150 grams per 100 milliliters of water times, I'm running out of room, a million. What do you get? $15 parts per million of copper. So you see how that's like an easy number to look at, 15 parts per million? It's easy to think about, it's easy to look at. That's why we do that. Because if we did that as a parts per 100, as a percent, it would be really small and it would be really hard to think about. But this way it's easier to think about. Okay. All right, now this is something that is going to come in really, really handy for y'all. So a lot of times you're going to be working and you are going to need to prepare solutions, right? You have to prepare an IV for somebody with a certain concentration of something in it, or you have a reagent that you need to use for a test and you're going to have to dilute it. So you have to understand dilutions. So a lot of times you have to think that if you stored everything that you need to use at the concentration you wanted to use it, your storeroom would be overflowing. It would be too much because it would be a huge volume. So what do? We buy things that are highly concentrated, right? And then I can keep this small stock bottle that's 100x, right? 100 times the concentration that I normally use it. And then I can just take a little bit out, dilute it in a large volume of water or whatever it is, and I'm ready to go. But I only took up a little space in my storeroom. So you're going to see this often, very, very, very often. So while the formula is here, so if you look, it says dilution equations, the very first one under dilution equations. If you just know this offhand, it is going to help you out so much. So what is my formula? My formula is my concentration initial times my volume initial equals my concentration final, volume final. Sometimes the C You might have learned this in chemistry as M, right? MV, right? Or it doesn't matter. Concentration and molarity, it's the same thing. But in this book, we use the concentration one. So our initial is always going to be the stock container. So the stock container is very high concentration. The final is going to be whatever your working solution is. Right? So that's like the 1x. The stock is like the 100x. The working solution is the 1x. You can do every single dilution problem with this equation. Okay? So how many liters of a half normal saline IV solution with a concentration of 0.45% mass by volume can be prepared from 1 liters of a 9% mass by volume stock solution? Okay. Which of my numbers in here are my initial stock concentrations? The 1 liter and the 9% is my stock. So then what is my working solution? My working solution, my final. I only know what? I only know this is concentration. I don't know volume. I'm trying to solve for volume. I'm trying to solve for liters. So all you have to do is figure out what goes where and then plug it into the right place. So my initial stock is 1 liter, right, of a 9%. So 9% is our concentration. 1 liter is our volume. Then we're going to do our working solution. Our working solution we know has a concentration of 0.45%. Now, you can leave off the mass by volume because they're the same. If they're both mass by volume, you're good. So always double check that your units are the same. Then we don't know our volume final. That's what we're trying to solve for. So we divide by 0.45. Divide by 0.45. What do you get? $20 what? And I'm going to put a point there because those two should be significant, right? $20 what? Liters, 20 liters. So be careful. What if the question asked you how many milliliters? Then you would have to convert it. So just be careful that you have the correct unit that they're looking for. Okay. A patient order requires 1 liter of a benzyl alkyl chloride antiseptic. You have a 12% stock solution. How much stock solution will you need to prepare the order? I mean, this is literally something that you might actually have to do. So what formula are you going to use? CI-VI, CF-VF, right? So what are my initial? My initial is my high or low concentration. It's your stock. It's your very high concentration. So I have a 12% stock solution. So I'm going to say that's 12% is my concentration. Do I know the volume? No, that's unknown. It's asking how much stock solution will you need? So that's unknown. And then do I know my final? Yeah, I know both the volume and the concentration. So it's 0.5% is my concentration times 1 liter. So what do I get? VI is what? What do you get? Should be small. 0.42. So we have 2 sig. Well, we really only have 1 sig fig, but gosh, that's kind of terrible. Let's leave it at 2. So can you go in the storeroom and measure out 0.042 liters? Right, that doesn't make sense, does it? So what would you do? What would you actually do? Convert it to milliliters. So in order to convert it to milliliters, I would say in 1 liter, there are 1,000 milliliters. So move your decimal place 1, 2, 3 times, you get 42 milliliters. So you would put 42 milliliters of this antiseptic plus how much water? How much water? The order requires 1 liter. Do I put a liter of water? No, I do not. What do I put? I put a liter, which is the same thing as 1,000 milliliters minus 42. So what do I put? What do I put? 958 milliliters. Be careful with that. Because if you just put a liter in, you have less than a 0.5% solution. And then maybe you're not creating this sterile antiseptic that you thought you were creating, right? So be very careful about that. Okay. All right, how would you prepare 2 liters of a 1 molar magnesium chloride solution from 5 molar magnesium chloride stock? What am I going to do? Same formula, right? CIVI, CFVF. So what are my initial? My initial is my stock. Which one's my stock? The 5, so this is my stock. What's my final? Right? Okay, so now when I go and plug this in, my stock, I know I have 5 molar, that's my concentration. Do I know my initial volume? No, not at all. So it's my unknown. CF, so my concentration final is 1 molar. My volume is 2 liters. So VI is what? .4 liters. Now, how would you prepare? This does not answer that question. So you have to actually explain, how would you prepare this? So would you tell somebody to go and measure out 0.4 liters? No, what would you tell them? In 1 liter, I have 1,000 milliliters. So I have really 400 milliliters. So now, how would you prepare it? You would add 400 milliliters of my 5 molar MgCl2 stock to what? I want a final volume of 2 liters. 2 liters is the same thing as 2,000 milliliters, right? And I'm going to subtract out my 400. This is not the water, this is the total. This is my stock. So I want my final water to be what? 1,600 milliliters of water. So I'm going to add 400 milliliters of 5 molar MgCl2 stock to 1,600 milliliters of water. Right? So be careful with that. Okay. So this is really similar. You have to prepare 400 milliliters of a disinfectant that requires a 1 to 8 dilution of a stock solution. How much of the stock solution will be required? So you have dilution factor things here. You have a formula over here, but you don't really need the formula. You just kind of need to think about it. So what is a 1 to 8 dilution? A 1 to 8 dilution tells me that I'm going to take one part and I'm going to dilute it into 7 other parts. And I get a total of 8 things, right? So have you ever seen like the can of chicken noodle soup, Campbell's chicken noodle soup, right? If you take a can of chicken noodle soup, what does it say on the back of the chicken noodle soup? Add 1 can soup to the pot and then do what? Fill it with water and add another can of the water to the soup. So what did you do there? What kind of a dilution did you do? If I have my soup and I put 1 can soup and I put 1 can of water, what did I do? I have a total of what? I have 2 total. So I did a 1 to 2 dilution. So it's how many parts were the soup and how many parts are total. That's what a dilution refers to. Parts to total, right? So if you do a 1 to 8 dilution, how much of the stock solution will be required to make 400 milliliters? So all you have to do for these is to take your final volume. I want 400 milliliters, and I'm going to divide it by my dilution. So how many total parts are going to be there? 8. That's it. That's all you have to do. What do you get? 50. So you're going to take 50 milliliters of your stock, and I'm going to add that to what? 400 milliliters? No, what am I going to add it to? 350 milliliters of water, or whatever you have to dilute it with. It's the same thing that we were talking about before. Then we get a total of 400 milliliters total. Okay. So just remember that whenever you're given a dilution, that big number over there tells you the total, not the parts. It always tells you the total. Okay. All right, last, we're getting to the very end. Oh my goodness. Yay. What's that? Good. Question? Can what?
Where did they get 350 for the water?
Come down. So because the 350 comes from, you want a final volume of 400, right? So 400 minus however much I'm going to put in of my stock, which is 50, gives me 350 milliliters of water. So this is my final volume. This is my stock. And then I get my water, because my stock plus water should always equal to final. Yeah, it's a good question. It's a good question. Everybody else okay? Question? It's okay to ask. Okay. Always okay to ask. All right. Osmosis and diffusion. We kind of talked about this at the very beginning of the chapter, right? I think it was the beginning of the chapter. But when we talk about osmosis and diffusion, osmosis is the diffusion of water, right? So remember we were talking about red blood cells and what was going to happen with red blood cells if you drank salt water, right? What was going to happen to your cells if you drank salt water? I have my red blood cell, right? And I drank tons of salt water. I would have tons of salt particles all over, right? But I only have a few on the inside of my red blood cell. My particles can't move. My salt can't move. It's charged. It can't just diffuse across the membrane, but water can. So what's water going to do? My water is actually going to leave the red blood cell. My water will exit. Water will exit cell. The cell is going to shrivel up, right? That's a problem. That's a big problem. That's why you can't drink salt water. So when we talk about that, we use some terms that are hypertonic and hypotonic. You've heard that before, right? Probably in biology, you've heard of hypertonic and hypertonic. So when you're trying to remember which one is which, do I want to describe? You're describing the solution that the cell is in. So this is how I remember it. And I wrote this on, I did this in the video. But when we talk about something that is hypertonic, I think about a cat because cats purr, right? Let's see if I can do this. I'm a terrible, terrible artist, right? There's his nose. He's got whiskers and cat eyes, right? So I'm terrible. Oh, he's a chunky kitty, right? And he's got a tail. All right, it's good enough, right? Okay, so what do cats do? They purr, right? So when they purr, the purr comes out of them, right? So if you put a red blood cell in a hypertonic solution, what's going to happen? The water will move out. Ha ha ha, right? Okay, kind of cool. So if you put a red blood cell, that's what I drew here, in a hypertonic solution, the water will exit the cell. Okay, now the other way is, what if you put the red blood cell, my RBC, he's small, right? But he's got lots of salt in there and you only have a little bit of salt in the container. What's going to happen to water? Water is going to move into the cell to equalize the concentration of the solute. So water will move in. So how do I remember this? What is this called? Well, if I'm cooking, right, I'm going to pour water into my pot, right? So water goes into H2O into a pot. So the water will move into the cell. So this is a hypotonic, right? That's the PO, the pot, hypotonic. So this is hypo, PO, and hypotonic solution. This one was a hypertonic solution. What's the third possibility? They're equal. They have equal concentration inside the cell as inside the solution. So what do we call that? Isotonic. Isotonic. Okay, so let's try some of these problems. Let's do 8.48. A lettuce leaf in the produce aisle at the grocery is accidentally submerged in water. It's a national emergency. Will water exit or enter the lettuce cells? What do we think? You got to assume you're submerging it in pure water. There's no solutes there. It will what? It will enter the lettuce cells. It will enter the lettuce cells. Will the cells swell, get big, or will they crenate, which means they shrivel? They're going to swell. Now, is the tap water hypertonic or hypotonic to the lettuce leaf cells? What did water do? Water went in, like water goes into the pot, so it is hypotonic. See how hypotonic has the word pot in it? It's hypotonic. How you remember that? Telling you. I know it's crazy, but it works. All right. Why is this important? Like, okay, lettuce leaves and stuff like that, sure. But why is this important? So if you have a patient who has kidney failure, right? What's the whole point of your kidneys? To remove toxins from your bloodstream, right? And so in the process, it makes urine, and urine contains all those waste products, and you pee that out and you've cleansed your blood, right? So that's what kidneys are. They are blood cleaners, and they are super great at their job. If you have kidney failure and your kidneys do not work, you will go on what is called dialysis. So in dialysis, there are a couple of different kinds of dialysis. There is hemodialysis. Hemo refers to what? Your blood. So what they do is they take blood out from your body. They pass it through this machine that is enormous, that does what your kidneys do for you, and your kidneys are super tiny. So remember that your body is absolutely amazing because it can do with a little tiny organ what it takes us, a massive machine, to do. So the blood goes into the machine. Now, in order for waste products to leave the blood, you have to pass that blood through the machine where you have a low concentration of stuff so that all the waste products will diffuse over, right? But you have things that are important in your blood, right? I can't take everything out of a person's blood except for their red blood cells and put it back and expect them to survive, right? So you have to be very careful about that. So you have to make sure that things that you want to stay in the bloodstream have the correct concentration in the machine so that you'll have diffusion of particles, but it will stop once you get to the physiological concentrations that you want. So you have this patient who's undergoing hemodialysis. As blood is leaving the patient, if it leaves the patient, it has lots of what? Of waste in it, right? Lots of waste in it. It has what kind of an osmotic pressure? So when we talk about osmotic pressure, the more stuff you have, the higher the pressure is. So is this person going to have a high or a low osmotic pressure? It's going to have a high osmotic pressure compared to the dialyzing solution, and it has to, right? The dialyzing solution has to have less particles so that the particles will move over and exit the person's blood, right? Okay, so as blood re-enters the patient, what happens to its osmotic pressure? Remember, things are going to move to equilibrate to a certain point, right? So when the blood is going through the machine, things are going to diffuse until they get to equal concentrations. Once they get to equal concentrations on either side of this membrane in the machine, diffusion is going to stop. Then the blood goes back to the person. So is it higher, lower, or the same osmotic pressure? It's the same. It's the same. That's exactly right. So whatever the osmotic pressure of the solution in the machine is, it is going to be equal when it re-enters the patient, right? And we've made a lot of progress with hemodialysis in the last like 20 years. It's been amazing. It used to be kind of a death sentence, and it's not anymore. Okay, oh, here we go. Will a red blood cell undergo crenation, lysis, or no change in each of the following solutions? So how are you going to figure this out? There's something you need to know, right? In order to know if something's going to move one way or another, you have to know what are the physiological concentrations of a normal cell, right? This you need to memorize. You will need it. So you need to memorize this. So what are physiological conditions or physiological solutions? So we have a few. We read this earlier, 0.9% mass by volume NaCl, right? And 5.0% mass by volume D-glucose. The D-glucose is abbreviated D5W. Okay. So you're going to look, oh, I don't know how I did that. I did AA, BB. That's crazy. All right. If you have something that is 10% mass by volume NaCl, if you put a regular red blood cell, what's going to happen? Water does what? If your cell is normally 0.9, water will go out. Cell does what? Cell shrinks, which is called crenation. Distilled water. You know what distilled water is? You got no ions in it. You got nothing in it. So this is just like saying 0% NaCl. So what will water do? Water will go into the cell. What will happen to it? It will swell and eventually lyse. Undergo lysis. What do you want to say that? 5% NaCl. What's water going to do? It's higher concentration than what's in the cell. So water will go out just like in A. The cell will undergo crenation. Okay, a 5% mass by volume glucose. Nothing will happen, no change. Yay. You helped your patient survive today. So we got a little bit farther in chapter 8 than I was planning because the next class period still says chapter 8. So we will finish chapter 8 Tuesday, and we will start chapter 9. Okay, so you need to go in and watch. I'll go and change it online, but you need to go and finish watching 8 and then watch at least 2 sections of 9. Okay, and I'll change that on the thing. Y'all have a great rest of your day.